thematic session. One of the challenges when you get into environmental ecological information and data mining, if you will, is that there's a lot of things that end up crossing and overlapping and mixing in. But we're really fortunate on Georgian Bay and Lake Huron to have staff like Todd Howell, who is able to zero in on a number of really key issues, help to guide research in really meaningful ways, and then come out and present at places like this to folks like you. Todd Howell has been a Great Lakes ecologist with the Ontario Ministry of Environment, Conservation and Parks, for 28 years. Great speaker, an apt mind. Todd has sponsored and supported all kinds of different work on Georgian Bay, including the State of the Bay. Some Sturgeon Bay responses when they were going through some eutrophication issues with the Township of the Archipelago and many other research initiatives. We're really, really pleased to have him here. If you could welcome Todd Howell, that'd be great. Thanks. If you want to wander, there is an attachment.
Okay.
You think you're good?
Okay. First of all, a couple of details. Thanks to the organizers. I really appreciate the chance to participate in this, and I really, I don't know. The water of the Great Lakes is a boundless creature of fascination and value and beauty. So I like this. Second of all, I'd like to just start by saying thank you to David and Corey for their comments on climate change. I think the appropriateness and the significance is immeasurable. I am in the weeds with my presentation in terms of water quality details, and I find linking water quality to climate change somewhat difficult, but there is one overarching principle that I've come to see, and I see climate change in the work that I do around the Great Lakes, and that is water pollution problems of all sorts are worsened by climate change, and that's sort of a real-time overarching theme to take away. Anyway, in my presentation, I'm going to narrow in on the geography of the coastline of eastern Georgian Bay, and my theme is that this is a very unique environment with respect to coastal areas in the Great Lakes, and I'm going to attempt to go through some work that our group has gone through in the last few years, and take you along a trip to how we've tried to make sense of some things. If I can. So here's the outline. I'm going to start off with a little bit of introductions as to why we're doing what we're doing. But most of the talk is going to be looking at selected findings from a series of studies in recent years. I'm going to start off maybe a little tangential, looking at invasive species issues around mussels, because elsewhere in the Great Lakes, that is a defining feature of sort of ecosystem change and with a number of water quality ramifications. Then I'm going to get the meat of the talk. We'll be looking at how the geography and the geology of the fringe of eastern Georgian Bay shapes these pervasive gradients in water quality that have pretty profound significance and are just incredibly interesting and unique. And then finish off with just a few comments on Parry Sound, which is a special case of the coastal fringe, since this is Parry Sound. Okay. So the genesis of this work really goes back a number of years. In the early 2000s, the ministry conducted a number of synoptic water quality surveys of eastern Georgian Bay. The work was relatively successful in the sense that it painted a broad snapshot of conditions along the coastline. However, there was a significant limitation in the amount of temporal and spatial coverage. Water quality conditions were quite heterogeneous across the coastline, and it really limited the degree to which you could interpret who was driving the bus. So right from the get-go of that study, there was always intended a follow-up piece of work that would try to drill down into the dynamics of the relationship between variability in water quality and those drivers on the land and from the lake. This study has actually been conducted. It was conducted over, I guess, 3-4 years, and the write-up is still going on. It started in 2014. Now, the study itself, it's actually a package of studies. The first of which deals with nuisance algae, invasive species, what's known as benthification in the lower Great Lakes, and simply asking the question, is this a problem that we have to consider in the coastline of eastern Georgian Bay? Relevant? Do we factor it into a water quality work or not? The next part is a series of very spatially detailed water quality surveys, as I said, looking at the push and the pull of conditions and sort of describing water quality and trying to understand the dynamic. There's also some other work that I'm not going to talk about today, some biological work looking at biological indicators of water quality. And another thing that I feel it's useful to mention here, we put a substantial amount of effort into collecting physical data, which I hope in the fullness of time will serve as a valuable resource. These are current measurements, lake structure, things that people need when they're looking at physical conditions, or in the context of climate change, how physical conditions have changed. So there's a reservoir of information on that. And I also have to mention that there are the ministry also funded other studies with the Severn Sound Environmental Association, the University of Toronto, and other aspects of this broader study that are out there. Okay, ecosystem change due to invasive species, zebra mussels and quagga mussels. Now, in the lower Great Lakes, this is a really big problem. The lake gets, it's one of those things where I think, a quick video is helpful. This is Lake Ontario. Vast tracts of the coastal area overgrown with mussels and have a very, very, very substantial effect on the lake bed. Those effects are amplified within the water column. They manifest as reduced amounts of plankton. You'll hear more about that this afternoon, I expect. And they also change water chemistry features. Nutrient levels tend to go down, and you also have more nutrients and biomass on the bottom of the lake. And one of the phenomena that you expect, and we went looking for, is the blooms of benthic algae, a green algae called Cladophora. So basically the bottom of the lake comes alive. Now, so we started off with a series of diver-based surveys to look at what the lake bed of eastern Georgian Bay looked like. Looking for numbers of mussels and looking at whether we had a benthic algal problem. And this is what we found. And this is characteristic. There are mussels in some areas, but really not substantial amounts of mussel or algae. Let us play it. Okay. Now, what was really interesting is the fact that when we looked across the coastline, we found that there were a number of areas where mussel densities were either not present or in very low abundance. And what we figured out is that water chemistry over lots of the coastline is simply not supportive of mussels. There's not enough calcium in the water for the shells. And so that the distribution of mussels is very much shaped by how water quality behaves along the coastline. Now, so essentially the water coming off the Canadian Shield, which is mixing in the inner parts of the coastline, does not have enough calcium. The water out in the open lake does, and so it depends on where you are in that. Here, okay, this is a better way of getting it across, I guess. Okay, so we actually use Conductivity, electrical conductivity. I'll explain it right now because you're going to see a number of pictures. Electrical conductivity is simply a measure of how electricity moves through water. It is determined by the amount of ionic material in the water. So calcium, chloride, these things will conduct electricity. And so you can use it, you can measure it in the field very quickly, and you can then use it as a surrogate variable for other things. If you look up here, calcium is directly related to conductivity, and if you look down to the bottom here, you'll see that muscle abundance, there's no muscles below 140, and you have to get up to about 180, which is background open lake, before you really get any number of muscles. Now, I've depicted here, and this is something you're going to see a lot of, and I'm going to drone on about. This is the coastal fringe gradient. So this is conductivity. It's low, shield water, and it's high in the lake, the calcium associated with the limestone of the Lake Huron Basin. Yeah. Okay. Shore fouling algae, Cladophora. That was one of the targets. It's not a problem. Essentially, it's not there. Now, I'm going to show you a video of Lake Ontario. The point here is that there are areas of the coastline that have phosphorus levels no different than where I'm showing you the video. And I believe a lot of that is linked into this mussel effect. There we go. This is off of Scarborough in 2015, thanks to Environment Canada Climate Change Diaries for this. This is Cladophora. Like, this is not atypical. Much of the near shore of the north shore of Lake Ontario looks like that, and underlying that are mussels. Luckily, you have, this is prime Cladophora habitat, but you don't have the Cladophora. No. Okay. So, just to put this to bed, the mussel-related effects on the ecosystem of eastern Georgian Bay the direct effects do not seem to be particularly relevant here. You don't have algal fat, the bottom's not overgrown with algae, and you have low numbers of mussels. However, if you look at this problem in the broader context of Lake Huron and Georgian Bay, the mussel effect is very real. The problem is, in this particular instance, it's offshore and it moves inshore. The waters of Georgian Bay and Lake Huron over the last number of years have seen a reduction in concentrations of total phosphorus and chlorophyll A that have been linked to this mussel filtration effect. Now, so what I believe is relevant to this area is the fact that when the offshore waters move inshore through the embayment systems, you're now moving water in that has lower concentrations of algae, lower concentrations of nutrients. It's sort of a diluting effect. Now, okay. This is, to back up the point about this offshore reduction in productivity in the lake, which is well documented at this point in the scientific literature. I show you some work from what we call our nearshore reference stations around the Great Lakes. These are a suite of stations we monitor periodically. And what I'm showing on the top panel is phosphorus, and you're looking at the red star, which is the median value. You can see that median value tracked down. Last surveys were in 2015, so that's down around 2 to 3, and the same thing with chlorophyll. And this is not inconsistent with what's been seen in the open lake. So the offshore of the open lake is getting more nutrient depleted. Now, I think you'll hear some information later on that will speak to the fact that maybe this trend is sort of curtailed at the moment, but it was definitely part of the story. Now, going to switch into the water quality bit, which is probably why I'm here for the most part. The gradients. There is a pervasive, very intriguing gradient in water quality from the offshore to the inner parts of these embayments. And people who live up here and work up here know it, they observe it, they see it. And all I'm doing is sort of putting some numbers and some features to it. Again, a conductivity... Oh. Okay, too excited. A conductivity map, and these are phosphorus concentrations. For now, all I really want to do is to look at the two extremes. This is the offshore, it's the blue water. Very low nutrients, ultra oligotrophic, hard water. High pH, lots of calcium, very little chlorophyll. The near shore, the inner near shore, around here, it's much more productive. Oligotrophic to mesotrophic, lower pH, and higher phosphorus and higher concentrations of chlorophyll, just a different chemistry. Now that gradient is played out over and over and over up and down the coastline, the brown water. Okay, the concept here is not overly difficult at the high level. It becomes really difficult when you look at the details. You have mixing of offshore water, and the degree of mixing across what I call the coastal fringe depends on where you are. If you're out here, you get a lot of mixing. If you're in the inner side, you get more limited mixing. And so the degree of mixing basically shapes water quality across this fringe. And so what you see in a particular location is a function of that mixing to a great extent. Now, in a number of, this is sort of a process figure, in a number of the subsequent images that I'm going to show, you'll see things referenced to distance from the inner fringe. So what I've done is I've used these hatched lines to indicate the inner fringe. And these are survey lines. These are track lines where we've collected data in these areas. And the data collection points are referenced at 90 degrees from these fringe lines. So you'll see graphs that reference distance away from the fringe, basically distance offshore. These are our 4 study areas for the bulk of it. And there's more work that was done in Parry Sound as well. Okay. How do we collect the data? I hope you forgive. This is a recent slide from similar, exactly the same. It's from Toronto. But, you know, the track line, on the track line are a suite of sensors. Every 5 meters collects water quality information for about 6 or 7 sensors. And you see the track line, these are the data points. And so at the squares, you also collect water samples for chemical analysis, and you put them together, and you use mathematics, kriging analysis, and you create these data maps. And that's how the maps that I'm showing are constructed. Okay. Now this is kind of a rehash, just to bang away at the point here. This is again just the conductivity gradient, but showing that in each of these areas, the colors, the blue, low conductivity, the red, higher conductivity. And on top of that, I've also taken all the data here and I've used the multivariate statistical analysis just to boil it all down. And I draw your attention to the right side of the slide here to show how integrated the changes in chemistry are here. As you go into the inner parts of the fringe, phosphorus, chlorophyll, turbidity, silicates, and suspended solids go up. As you go into the open lake, nitrate, potassium, pH, sulfate, magnesium, and calcium go up or down, depending on where you are. So it's an integrated chemical gradient. Now, this is probably what you're interested in. This is the productivity nutrient richness question. And in essence, there is a very real productivity gradient across this fringe. These are chlorophyll concentrations. Red is high, blue is low. And again, in all of them, there is this gradient in concentration. This is for one set of surveys. On the right side of the figure, I've taken the individual survey dates over a seasonal cycle and plotted them as a function of this fringe distance. So basically, the low numbers here indicate 1 kilometer from the inner fringe, and this is 15 kilometers from the inner fringe. And you see in all cases, the concentrations decline across the range. It's just a way of summarizing the fringe gradients, which are they're variable amongst locations and times, but they're very much there. Now, phosphorus. Phosphorus does the same thing. Again, phosphorus concentration and distance from the inner fringe goes down. So where the problem comes here in terms of monitoring, because really one of the core reasons for doing all this was devising a methodology to monitor water quality to detect subtle changes in an area where there was very strong natural variability. The anthropogenic effect is interwoven with the natural effect. So now you have, in order to be able to sort chalk from cheese, you really have to have a strategy for predicting what the expected phosphorus concentration. And that is where I have spent many, many days racking my head trying to figure out a strategy, which I will lumber through in a few slides. Okay, so your options. You can go to guidelines and objectives, but it should be obvious at this point one number is not going to do it in this kind of a regime. You know, there are those you can apply, and some are higher, some are lower. It doesn't. The only one that's really I found insightful for just educational purposes is conventional trophic indices, which I'll show you in a second. Background, relative to background, what is background? The open lake, you can get background, but in the inner fringe, I'm not sure what background is. And I'll elaborate on why I don't think I know what the background is in a sec. And this is where we're going now, using surrogate variables. Variables that are correlated with the gradient, that are correlated with nutrients and chlorophyll, that might be used to predict what you expect to see under a natural variability regime. Okay, obvious candidates. Conductivity is pretty consistent as a gradient indicator. Water color, dissolved organic carbon, equally strong across the gradient. And the other thing which I've been working on, which is truly challenging, is chlorophyll concentrations are related to phosphorus concentrations. There's a predictable relationship. It varies, but can you use that relationship to predict what you would expect, how much phosphorus you would see or how much chlorophyll you would see, you know, irrespective of the anthropogenic effect? Okay, make a long story short here, we're mostly between ultra-oligotrophic and oligotrophic with some mesotrophic areas and very, very small areas of eutrophic right on the fringe of the boundaries. And this should not be a surprise based on the gradient as well, but you know, I've used spring total phosphorus and summer chlorophyll, pretty conventional measures. It shows that it illustrates the productivity gradient, but it does not have a great deal, you know, except for the verification examination of the areas that are in that range potentially, or further examination of the mesotrophic areas. Conductivity as a tracer. I've taken the same conductivity data I showed earlier, mapped it as a function of fringe distance. Here's the trouble. Water, and I draw your attention here, okay? We have very little gauging information on how much water actually comes out into the coastal fringe. And based on the one gauge that I can get data for that I think is relevant, what you see is a spring, early summer loaded discharge of water into the coastal fringe, and then not much until later in the fall. Now what that means, it actually shows up here in Technicolor, is that your gradients, your spring gradients are stronger, your concentrations, your conductivity levels are much lower, And so the gradient, the conductivity gradient, changes over the course of the year. As less water comes in, the lake starts mixing further and further in and more strongly with it, and it changes the actual specifics of the gradient. And when you look at total phosphorus as a function of the conductivity, oh, you throw your hands in the air and say, oh my, this is not going to work. Simply put, the relationships, there's always a relationship between conductivity and total phosphorus, but it's all over the map. And it's all over the map because of the way in which the water is mixing within the coastal fringe. And so there is an interesting story here, is that while DOC while conductivity is diluted out over the summer, phosphorus concentrations actually tend to go up or remain unchanged, which is a bit of a mystery and has some not positive connotations. Dissolved organic carbon is a much better story. It's not perfect, but it's much better. Again, DOC plotted as a function of the fringe distance. Again, these relationships, they're a little less variable. But again, you've got this, the blue line is early spring, and they're always down at the bottom. The strongest gradients are when you've got more of the brown water from the shield being washed into the system. Relationship with phosphorus is much better, but it's still variable to an extent. Now, but I think there is still some hope here. It just means you have to use these relationships confined to an area and confined to a space, but I think there's something to work with here. And then finally, this is the prediction of phosphorus. Okay. Now, as I said, total phosphorus and chlorophyll are, and this is typical of many, many systems. You know, you expect, because phosphorus is a limited nutrient, that the amount of algae will increase with it, and it does. Mostly similar, some differences. Moon River, for example, has a stronger slope here. I'm not exactly sure why. But anyway, the point here is you can use these relationships to predict phosphorus, and I have done here. This is a cog machine area. I have actually taken chlorophyll, I predicted phosphorus from the chlorophyll concentrations and mapped it out over the areas and for 5 different surveys. Now, first thinking was, okay, are there hotspots that jump? Are there areas that sort of stand out atypically? And short answer is not really, possibly. Down around here, you might take another look, factor in the DOC. I've also tried other kinds of mathematical magic, sort of looking at back predicting chlorophyll in that. And I'm still working on that. This is potentially something that might be useful, but at the end of the day, it's still a struggle. What's important here is that I've talked about chemistry, but this gradient is much more than chemistry. And how nutrients play out here are shaped by so many other things that we tend not to even consider. This is just exposure. Low exposure, high exposure. But if you look at, and I have looked at them, if you look at the light levels, dramatic gradients in light transparency and light levels, water movement, other key nutrients for algal growth, nitrates and silicates co-varying in ways which you potentially expect effects on organisms. pH and the levels of major ions, things which we know affect how things grow, also change dramatically across that gradient. Okay, I've got a couple minutes left before I get hooked out of here, and I'm going to talk about Parry Sound. Parry Sound is a kind of a mutated aspect of the coastal fringe. It's kind of flipped and varied. This is conductivity in Parry Sound. Now, again, you've got the backwater areas, lower conductivity. If you had it out here, you'd have red of higher conductivity out here. Mostly moderate to low conductivity. But chlorophyll. Here's the real story for Parry Sound that really kicked me. I believe Parry Sound is given what's happening in Lake Huron in Georgia, is an ecological reserve where there are nutrients, where there is productivity, and also, if you look at the conductivity relative to the surveys we've done for the mussels, I don't expect there are any mussels or very few mussels in Parry Sound. So it's a special pace. If you look at the chlorophyll, it's generally in the oligotrophic range. This is really good. Deep Bay is the only spot there where there's evidence of enrichment, and it's a sort of outlier, but in some ways that Deep Bay is very much a lake unto itself if you actually look at the way it's connected to Georgian Bay. Anyway, some phosphorus numbers. Basically, in terms of the variability within Parry Sound, it was actually turned out to be a bit of a snore, which was a surprise, with the exception of Deep Bay. Mostly all between 4 and 7, the oligotrophic range. And if you look up here, I've divided up the area into blocks. And then I've summarized 5 surveys, and these are total phosphorus numbers. And yes, there's a slight difference in the average between, the Menominee Channel, Inner Harbor, and Depot Harbor. I'm not even sure they would be statistically significant. And most importantly, not a single sample exceeded 10 micrograms per liter of total phosphorus. Now, okay, that's it, and I am going to say what I'm going to do next, I hope, anyway. My priority right now is getting this stuff formally reported, so you can all review it and sort of see whether it holds water or not. I'm still working on this approach for monitoring because I really hope to go back and actually try out some things in the coming future. And so, yeah, I am thinking about further field work, going to some of the areas we didn't, kind of a true test of approach. And I also thought we'd mention our reference stations. We monitor on a cyclical basis. We have surveys in Lake Huron and Georgian Bay slated for 2021, and those surveys are relevant in broader than water quality because we also do contaminant work in those surveys as well. And of course, a lot of people helped with this, and I would be remiss not to point out that this has been a big undertaking. Certainly, some of the people at Severn Sound have really been players over the course of the things. Also, Matthew Wells, Lashika Garangi, and Kevin Lee at University of Toronto. Physical work that's not been reported here, but a whole lot of physical stuff. And our own staff at EMRB have put a lot of effort into this. Thank you.
There's some really, really excited people over at this table, in large part because a lot of what you just heard we haven't heard yet and isn't in the last State of the Bay, and we just got a next chapter for the next State of the Bay. So this is awesome. We have time for a couple of questions, if there are any. Elena.
Have you been monitoring any of the nutrient runoff from the Parry Sound 33 fire, or do you have any predictions for how that'll affect water quality at all?
The short answer is no. We work in other parts of the Great Lakes. Predictions how it would affect? Anytime you mobilize material in a river system, you're going to bring nutrients in. So I would expect there's probably a nutrient related. How the question that always comes when you ask runoff related things is how biologically available and relevant is it just refractory material or not? It's an interesting question. You don't have to guess though. Years and years ago, the experimental lakes area up in north of Kenora experienced some pretty significant fires around their experimental lakes, and there's a literature there you can go to see what might be going on. But yeah, that's best I can do.
Okay, my question is Georgian Bay, Eastern Georgian Bay Fringe, is it your dream research lab or your nightmare?
Oh, I've worked around coastal areas all around on Canadian Great Lakes, and I have never been challenged, but it is sort of, it's beautiful. It's not beautiful. I'm talking from water chemistry, the water chemistry challenge. It's beautiful. Like it's so interactive and so dynamic. The real problem is one of the big pieces is missing. We do not know what's coming into that system. In order to take apart the water quality, you've got to monitor quantity and quality of tributary input to the system. And until you do that, you're not going to move the bar a lot more.
If you were to prioritize tributaries that you want discharge data from, what would they be?
Well, I mean, I guess there are the obvious ones. Moon River. I mean, you've got the quantity, but you don't have the quality. I'd like something from the Sequent. I've been trying to get some. We monitored in 2016 this lower downstream of the Sequent River, but we don't have any particular. Beyond that, I'd have to take a map and look at Magnatawan. Yeah. Like, I mean, the bigger inputs to the system. It'd simply be a matter of watershed and quantity at this point. Watershed size and quantity.
Todd, thanks so much again. So I'll remind folks that if you do have questions, either you can put them up here, but we'll be shortly moving into our breakout session where you're able to write those questions on the table. But if you have a specific kind of bug and you can't find Todd, write your question up here. We're going to invite David Sweetnam back up to the podium here. Just a little bit more about David. As he mentioned earlier, he's developed and grown the invasive Phragmites eradication program for Eastern Georgian Bay with Georgian Bay Forever to protect Georgian Bay's coastal wetlands. It's a highly successful community-based approach. It's involved working with many stakeholders, volunteers, governments, and staff to meet the mission of Georgian Bay Forever to protect the precious waters and aquatic ecosystems that we find here. I'm pretty sure that one of David's happiest places is on the Georgian Bay Keeper boat, which I'm not sure if there'll be a picture of here. So welcome back. Thanks, David.
Thanks again. So now the good news. First of all, Georgian Bay Forever did a climate change declaration. So as an organization, we identified 4 activities that we would focus on. First is conducting research to better understand this threat to Georgian Bay. Second is educating the Georgian Bay community about climate change's causes and consequences. Third is working with volunteers and other organizations to reduce, mitigate, and remediate the impacts of climate change in Georgian Bay. And then fourth, and this was kind of an important one for our organization too, and that is to encourage individuals to actually engage in social and political action. So as a charity, we are completely apolitical. We're not doing partisan work. We are doing policy work. We are doing work that actually has an impact, positive impact in our aquatic ecosystem. And that's our focus. So one of the new tools that we've got that can actually, I think, Todd, this is an exciting one, not just for us, but for lots of scientists on the Canadian side of the Great Lakes, is this new vehicle. It's called an autonomous underwater vehicle. And it's basically a little 6-foot-long submarine, 6-inch tube, loaded with about half a terabyte of storage. So we can take over 300,000 sample readings per 10-hour shift that we put this into the water and send it off on its way. And it's got a sensor pack on the front end, the black end there, of sensors that will measure things like dissolved oxygen and pH and total dissolved organic chlorine, dissolved organic carbon, and then chlorophyll, all of the things that Todd just mentioned, needing to start looking at the water quality in Georgian Bay. So we can measure it with this device. We actually have named it, too, affectionately, Georgie McBayface. This is in homage to the United Kingdom's Bodie McBoatface that you might have heard about, the same kind of yellow AUV that they use in Antarctica because they weren't allowed to name their new research vessel. This was the internet top name, Bodie McBoatface. So Georgie McBoatface is GBF, you can see in there too, Georgian Bay Forever. But this is the kind of information that it'll give us. Three-dimensional, it can go up and down through the water column, it can run lawnmower paths, we can measure all of these parameters. Every second it logs the data, and so this will be a remarkable evolution in our capabilities in the Canadian Great Lakes. It's the best instrument of its kind in Canada. It's basically one of only three. This is the only one of its kind in Canada right now. One of three AUVs that Department of Fisheries and Oceans and Environment Canada have. By the way, I should mention, we did that purchase in partnership with Western University, the University of Waterloo, and Wilfrid Laurier University in Georgian Bay Forever. We pooled our money, and we actually produced this instrument. So we have access to a lot of research at the academic level too now. The other thing, as Greg mentioned, is our work on Phragmites eradication. Of course, that's this huge reed that's invaded our space, grows 18 feet tall, literally blocks access to our wetlands from our native species. Imagine a turtle trying to crawl your way from the water into a wetland area where you want to lay your eggs or up on some dry land. It's just physically impossible, and we find lots of dead animals in it. We've been working on this since 2011. We started to formulate our program, hit the ground running in 2012 with some financing from Environment Canada. But we've been just educating the public. And the neat thing for me is when we first started it, nobody even could understand what the word was. And now most people know how to properly pronounce it. So you can kind of use that as a scale of how effective we were being on our public communications. And it's a fantastic community-based program that brings lots of people out to become frag busters. You can participate in a number of events. And Brooke, if you want to stand up, ran our program in Georgian Bay this year. She oversaw our 5 students, and we cut a lot of frag this year. So thanks, Brooke. Again, we go out and train municipalities. We actually run the program for Tay Township, the Township of Georgian Bay, the community-based program, the Township of Georgian Bay, and now the Archipelago has come on. So we're really excited with that evolving partnership. This is a before, during, and after view of these machines, the truck saws that we brought in. These are like big mechanical cutting devices. I'll just back that up again. That's before, during, and after. And so in one season, we were able to clear that whole wetland out from basically 18-foot tall Phragmites. This year, we had nesting ducks, lots of waterfowl, tons of frogs, turtles, everything coming back into that wetland. So we can eradicate this invasive species, but it does take a lot of time and effort. This is in Collingwood, and again, similar, where we actually can reconstitute the wetland and access for our native species to come in from the outer waters and into the inner waters. This is another Lighthouse Point down in Collingwood. So if you haven't yet engaged in an opportunity to come out and help preserve and protect our wetlands, we welcome you in the coming years to get engaged and come out. But how many of you have actually come out and cut frag? Awesome. See that? This is phenomenal. Such an engaged community. So climate change is contributing to this loss of biodiversity. One of the other things that's happening in our waters is plastic pollution, right? And we're all used to these conversations when it's about the Pacific Ocean and the Pacific Gyre and the garbage patch and all that stuff. But did you know that on a per volume basis, the Great Lakes have more plastics and microplastics in them than the Pacific Ocean? So we still have work to do here. This is a fish on the US side of Lake Ontario, right? And that's just one of those drinking rings that it got stuck in. This is 2 jars here, but that's 1 load of laundry. So everybody's familiar with the lint trap in your dryer that you need to clean out after every time you do a dryer, right? And all the lint that comes out of it. A lot of that is the fibers, polyester, plastics, basically, that come off of your clothing, right? But your washing machine doesn't have a similar kind of filter on it right now. So when you wash your clothes, that just goes right down the drain and into the wastewater treatment plant, and most of that is captured, about 80%, but the other 10 to 20% goes right into the discharge in Parry Sound. Not because Parry Sound system is worse or not operated properly, it's operated just exactly as it was designed to be operated. It was just never designed to remove these kind of small particles from the water. So we're looking at a project called Divert and Capture, where we actually have installed in Parry Sound in 100 volunteer households. Is there any volunteer here? Fantastic. So we have volunteers in the community that let us into their laundry rooms to put these filters in place. And those volunteers now clean out the microfibers every 3 weeks, 4 weeks, whatever it is. And then Brooke is coming around now and picking those samples up. We're taking them to the University of Toronto to weigh and characterize the fibers that we're trapping in these filters. And we have already started measuring, before we put the filters in place, what the wastewater treatment plant was putting out into the bay here, and after the filters went online, and we're already seeing a decrease in the amount of fiber that's entering your water right here. And that means less fiber that's going back into your water intake and coming through your tap into your glass. Did you know you eat about 1 credit card per year of plastic? That's the equivalent. Oh, a week? Oh my God, that's even worse than I thought. That's even worse than I thought. 1 credit card per week? So anyway, that's the idea. We want to get rid of that from your system. Thank you again to the volunteers. It's fantastic. We've actually just been asked by Collingwood, invited down there to try to do the same program, and we'll look at about 500 families down there to start. And we're hoping to expand the program to double it in Parry Sound. So this will all be written up as a report by the University of Toronto, and we'll be bringing those results back to the community. Part of the activities of that too, I should mention, are shoreline cleanups, and we're inviting people to come down to their shoreline and help clean up the garbage. A lot of the materials that we're finding are things like cigarette butts. Cigarette butts are microfibers, and those cigarette butts are designed to capture chemicals, right? When somebody's smoking, hold those chemicals. Well, guess what? Those get thrown on the ground, sidewalk or the street, they wash into the storm sewer, and they go directly into the bay. And then the chemicals that are in those can leach into the water too. And also dock foam. Dock foam, we're finding tons of little bits and pieces of dock foam. So those are the projects that we're working on. Georgian Bay Forever is focused on protecting and working on water levels, water quality, and ecosystems. So we're happy to continue to do that for you, and thank you for the time to give you a brief update on what we're up to. Thanks.
Okay, so this is your turn. Well, actually, before we get there was a question that came up earlier from somebody from the audience, and I have to go over it, so I can't read it quick. The question from a few ago, which is why do wetlands continue to dry up alarmingly while the bay water rises? So, where's Corey? Where's going? So I'm going to take a stab at this. Unless, Katrina, you want to take a stab at it. Oh, I knew she was going to say that. Really quickly, there's different kinds of wetlands on the coast. There are coastal wetlands, and there are an incredible number of coastal wetlands. And those wetlands are influenced by the fluctuations in water levels of Lake Huron. So, 5 to 8 to 10 years ago when water levels were low, you would have been reading about and hearing about, there was lots of studies done around wetlands that were dried up and losses of biodiversity and productivity from those wetlands. It was a big concern. Now with water levels coming back up, there's a multitude of concerns that are coming with that. David touched on some of them, which is the rate at which the water has come up and the ability for species to respond and get back in there, especially if all of a sudden, in 2 or 3 years, the water levels go back down. So those are some of the complications of our Georgian Bay coastal wetlands. But if you step onto the shore of Georgian Bay and you walk inland, or who's flown over the eastern coast of Georgian Bay? Who's been lucky enough to fly over the eastern shore of Georgian Bay? So I got to go up a couple of years ago, and when you fly over inland, just inland of our coastal rock fringe, often, you will see an incredible abundance of near shore, inland wetlands. And so those are the wetlands often that I think that Corey was talking about in terms of drying that would be of the most concern. that those wetlands, if they're not getting enough flow, are drying up, or then, as per this past year, too much water and beginning to flood. So it's just that massive amount of variation. So it's not the coastal Georgian Bay wetlands, but it's those ones that are just upland of Georgian Bay. And there's some really important connections between those wetlands and the coastal embayment around total biodiversity and productivity of the coastal Georgian Bay. Sound good? Is that good enough? Okay. Now it's your turn, not my turn. We're going to move into our nutrients round table or table conversations. So you'll recall that in your program, I don't have an example of it right now, but in the program, if you turn, you will find for nutrients, the summary. There's 5 points there that have been distilled from conversations with the likes of Todd, from background research work, and been distilled as, these are what we think of as the 5 priorities for going forward. But what we want to hear from you is, what are your questions about nearshore nutrients or offshore nutrients? Do you have questions that you just don't, or have you seen things where you're confused about the nutrients, or algae in the bay, or perhaps your lake? And this is your opportunity to sort of answer those questions, and broadsheets have been provided. If you can have a table discussion, we might ask table 5 over here, if you could join in with table 3 over here, make a more fulsome discussion. And just have a conversation about that. We do have a number of Biosphere staff who will be walking around and hopefully able to answer some of your questions. And if we can't answer your questions, I'm pretty sure there's somebody or some buddies in the room we can bring over to your table to answer your question for you. And so, here's what your task is. Find a note taker, somebody who's hopefully relatively neat of script. Ask them to sort of take notes, have a nice conversation. Please take the time to listen to each other, so don't necessarily consume all the time. So if we had a talking stick or a talking feather at your table, you would be respectful and pass that around to everybody so that everybody gets a chance to listen at the table. And then really listen to what each other is saying, and then try to come up with some of those priorities or questions and say, here's what we feel. If you want, draw on the map of Georgian Bay, say, you know, here's a specific area where my cottage is at, and we'll go from there. So, this is your turn. Have at it, and we'll be walking around. And then we'll give just a heads up when we're getting close to lunch. All right? Thanks so much.